Projectile motion is the motion of an object in a parabolic path whereby the acceleration of that body follows a tragedy, and that tragedy is known as a path of projection. Now, when dealing with projectile motion can be applied both in sports and in warfare. During sports, we apply projectile in example like a thrown javelin, a thrown discus, and a ball that is kicked, a kicked ball. And during war, we apply projectile in a stone released from a catapult, and a short arrow, a bullet fired from a gun, a thrown or launched missiles. These are still application in warfare, but projectile motion is characterized by two axes, and these two axes are the y-axis, which is known as the vertical component, and the x-axis, which is known as the horizontal component. So these are the two axes that characterize the projectile motion. So when you have a projectile motion could be motion of an object that is launched into space and is free to move under gravity. For instance, you have this as a motion of an object. This object is launched and it moves in a parabolic path. This path is the u, which is the vertical component of velocity, where here you have the x, which is the horizontal component of velocity. At this point, the object attains a maximum height, which we call the h, maximum height, and this is the resultant of the velocity, which is u, and this part to this part represents the range attained by the projected body. Now, there is a need for us to know the time of flight, that is the time taken by this projected body to return back to the same level at which it was projected. So how do we get that? That is this line that goes from here to here. Now, at maximum height for a projected body, the final velocity is going to be what? 0. So now follow this sketch, bring out this from this sketch. You have this net or magnitude of the velocity, you have the vertical component of velocity, horizontal component of velocity, then you have this alpha, which is the angle of projection. Now this is u of y, u of x, the magnitude of the velocity, angle of projection. Now if you look at this, I use dotted line, which shows that what two parallel lines are equal. This part, which is u of x, is still same thing as this part, which is u of x, and this from here to here, which are parallel line, is still same thing as this part, which is u of y. So if you deal with this now, we can resolve the vertical component of velocity, which is u of y. And if you are going to do that, you follow the trigonometric identity SOHCAHTOA. If I go with SOHCAHTOA, from here now, we are dealing with vertical component, which is u of y. We are dealing with u of y. So u of x is not needed now. So if you look through this, what we have here is opposite over hypotenuse. We are not dealing with u of x, no. So opposite over hypotenuse gives so from this you can have, we are resolving the vertical component, sine alpha equals to opposite over hypotenuse, and opposite is u of y, hypotenuse is u. So here now you can have that u of y, if you make u of y the subject of formula, it will be u sine alpha. Call this equation 1. Same way, we'll resolve the horizontal component of velocity. So resolve again. Resolve the horizontal component of velocity. Horizontal component, which is our u of x. So if you follow the trigonometric identity again from that first sketch, now we need u of x. So this is not needed now. So we are working with opposite is not needed. We are dealing with adjacent over hypotenuse, and that gives us k. So bring that here, adjacent over hypotenuse. Adjacent over hypotenuse cos alpha equals to adjacent over hypotenuse. Adjacent is u of x, hypotenuse is u. So make u of x the subject of formula. U of x will give you u cos alpha. Take that as equation 2. Now we need to talk about the time of flight, which is capital T. Now, time of flight of a projected body is the total time taken for that projected body to return back to the same level at which it was projected. The total time taken for that body to return back to the same level at which it was projected. So for me to derive the equation for the time of flight, you have to record that. Record that V equals to u plus at. This is first equation of motion. V equals to u of plus at. Now at maximum height, v is going to be 0. Now time of flight takes place on the vertical component of velocity, so u there becomes u of y. The body is thrown up, a becomes negative g because it is going against gravity, and your t becomes time taken to reach the maximum height, not the time of flight. This is the time taken to reach maximum height. Time taken to reach maximum height, that is t. So we can have this as, put the value of all this into this equation. So we have 0 equals to u now becomes u of y minus, because a turns to d and t. So take this u of y to this other side, that gives minus u of y equals to minus gt. Negative here cancel negative, so we'll be left with u of y equals to gt, but u of y is u sine alpha. That's our equation 1. So put that back into this last step. So you have u sine alpha equals to gt. Make t the subject of formula. T becomes u sine alpha over g. Call this equation 2. Equation 3. Equation 3 is known as time taken by a projected body to reach maximum height. Now, but time of flight, which is capital T, is time taken to reach maximum height plus time taken for the body to return back to the same level at which it was projected. So T now becomes twice of small t. So therefore, big T, which is time of flight, will be 2 multiplied by what we have in equation 3, which will give us 2u sine alpha over g. Call that equation 4. So this equation 4 gives us the expression for the time of flight of a projected body. Also, we can also calculate the maximum height attained by that projected body, since we have the time of flight now. So the maximum height, for maximum height now, maximum height attained, which is h. You can just have it and record that v squared equals to u squared plus 2ax. This is third equation of motion. Now at maximum height, note v will become 0, then height is taking place on the vertical component, so u also becomes u of y. Now as the body is being thrown up, going up, the a turns to negative g, and then since it's gaining height, distance turns to h. So we put all this back to this equation. You have this as 0 squared equals to u squared now is u of y squared minus 2gh. So you have 0 squared equals to u of y is u sine alpha, which is going to be squared minus 2g with h. Take this to this other part, that is u sine alpha, take it here, it becomes minus open bracket u sine alpha squared equals to minus 2g with h. So from here now, make h negative cancel negative, make h the subject of formula. H becomes u sine alpha squared over 2g. Now we can open this bracket. This is still same thing as u sine alpha multiplied by another u sine alpha, all divided by 2g. So that shows that h equals to, here you have u times u, which is u squared. Note sine alpha squared is taken as sine square alpha. So I'll put that here. Sine alpha times sine alpha is sine alpha squared. So that becomes sine square alpha over 2g. Now this gives the expression for maximum height. Take this as equation 5 again, where u here is your initial velocity, and this is the angle of projection, and this is the acceleration due to gravity. Now maximum height is attained when a body is projected perpendicularly, and that is talking about 90 degrees. So for maximum height to occur, a body must be projected at an angle of 90 degrees. So if the angle of projection, let's say alpha, is 90 degrees, then you are going to have h to be u squared sine alpha squared over 2g. That gives h equals to u squared, open a bracket, sine 90 degree squared over 2g. Note sine 90 is 1, so 1 square is going to give 1. Then you have h here to be u squared over 2g. Now this is known as maximum height attained by projected body. Call that equation 6. Again, we can calculate the range of a projectile. Range here, r, range is range is the horizontal component of velocity multiplied by the time of flight. So range here gives horizontal component, which is u of x. U of x is u cos alpha, equation 2, then multiplied by time of flight, which is our equation 4, 2u sine alpha over g. So bring that to this part. We can have this as range now will be u times u. You have u squared, then you are left with 2 sine alpha cos alpha divided by what? G. Now 2 sine alpha cos alpha is a trigonometric identity which has a value, but we can just check through using this normal double angle formula, which is sine a plus b. We can use this to check. Sine a plus b will give us sine a cos b plus cos a sine b. So let a be equals to b. That is, anywhere I see a, I can put this. So I have sine a plus, instead of b, a equals to sine a cos a plus cos a, again sine a. Now this gives sine 2a, right? Yes, equals to sine a cos a plus cos a sine a. That will give me 2 sine a cos a. But let a now be taken as alpha, so that may give me sine 2 alpha equals to 2 sine alpha cos alpha. Now that 2 sine alpha cos alpha looks exactly like the expression that we have here, and the trigonometric expression for 2 sine alpha cos alpha is sine 2 alpha. So therefore range will now be equals to u squared sine 2 alpha over g. Call this equation 7. Now we have equation 7, but it is possible for us to have a maximum range. Maximum range occurs when the angle of projection or the angle of projectile of the projected body alpha is 45 degrees. That is angle for maximum range. So recall that range itself is u squared sine 2 alpha over g. So range becomes u squared, we are looking for maximum range, sine 2 of alpha means 2 times 45 degrees over g. So range now gives u squared sine 90 degrees over g. So you have range to be sine 90 is 1, so therefore you have u squared over g. Call this equation 8. This is known as maximum range. And remember, range is measured in meters, which is the total horizontal distance covered by a projected body as measured from the horizontal projection plane. That is in meters. Same way, height is also in meters, while time of flight is in seconds, and also time to reach maximum height is also in seconds.